to the EMS world, the aesthetic of EMS.
两只然后合在一起，
Yeah, I think it is not a big problem. Okay, Dr. Robin? Okay.
Well, thank you for inviting me. I've never played the Las Vegas ballroom, so I'm not sure how good I'm going to be at walking around. My pointer will work, but my eyes can't see from the back. So if you don't mind, I'm going to stand up here. I'd like to say next. I get confused, two hands. The last time I talked in Malaysia was 4 years ago. In fact, the last time I talked in Malaysia, I uttered the word EMS. I'm sorry I ever uttered it. I guess because it's mostly English speaking here, it got picked up. And EMS became the term used around the world when in fact we should have been using APIS. And I honestly haven't had much to say for 4 years. We really have undergone a period of a loss of confidence. Now, 4 years ago, I was too confident. I talked about sustainability. I talked about how we had this thing whipped. And then this EMS thing came along. I lost my confidence. And certainly from the South, we used the term mojo. My mojo was gone. But today, I think I'm getting the mojo back. I think in Thailand we're getting the mojo back. CP is getting the mojo back. So I kind of want to go through our story of how we got the mojo back and what it means to you. Because if Thailand can get the mojo back, so can Malaysia. So I had a title of a talk a couple of weeks ago, and it was Understanding EMS, Can It Be Stopped? And then last week, someone told me I had to change it for today. So I came up with a new title, Successful Shrimp Farming in an EMS World. Yes, the EMS world is getting larger and larger. There used to be just 4 members of the club. Now, unofficially, I think there's at least 15 or 20 members of the club. So we really are in an EMS world today. Next. So I always started the talk with the conclusion. And this was in the talk a couple of weeks ago where it's, can it be stopped? Well, yes, it can. I took a trip to southern Thailand maybe in May of this year, and I saw one successful harvest after another. Farmers were telling me they were making more money than they did in 2010. There was a lot of success, and this just shows one of our customers, but there's others that aren't our customers, but our customers are doing well. Nice large shrimp, very profitable crops. Next. Next. And then 2 weeks ago, I took a leading Ecuadorian farmer to visit some of our farms, and he witnessed this harvest, a 54-gram shrimp, 105 days, 22 tons per hectare. That farmer's eyes are still on that farm. He could not believe it. 54 grams coming out of a production pond. You know, in Ecuador, he said he had never seen a 54-gram shrimp. Next. And then last week, I took another little group from DSM. We had a little meeting with DSM last week. I took them around. Another harvest, 30 tons, 1 hectare pond, 115 days, 54 grams. These are not unusual anymore. We've got our mojo back. How did we do it? Next. I think I always start from a historical perspective. History repeats. It repeats in different ways, but it does repeat. So I plotted out Malaysia. Now, the numbers may be different, but the trend is the same. We started out in 2001 at under 30,000 tons. Then Vanami comes in, and we peaked around 90,000 tons. And then we've been in a slide since then. If we remember here, what happened? Why did we go from here to here? We had to change. We had to learn, and we had to change. Next. So let's look at the deja vu. 2001, I'm going to show Thailand slides, maybe similar in Malaysia, but I'm going to do Thailand. This is what I came back to in Thailand in 2001, a failed monodon industry. It was going nowhere. Next. So we were sourcing wild broodstock, and clearly from my experience from the Americas and other places, the problem was that, the broodstock, the wild animals, the non-domesticated stock. So we changed. 2002, Thailand changed. We moved to nuclear breeding. We established several nuclear breeding facilities to produce disease-free, healthy broodstock. We then learned biosecurity against our number one enemy then, white spot. So we put in biosecurity. And we learned with healthy shrimp, white shrimp, all of a sudden the biomasses got too big for our aeration. So we had to add more aeration. We learned and we changed and we created success. Next. So, to have success, I have one rule. It's got to be simple. Complexity doesn't work. If we want whole industries to change, it has to be simple. It has to be straightforward. And it has to be cost effective. This is what I left in Guatemala when I left the Americas. Poor quality seed, different sizes, full of all kind of unknown evil things. And so we bring in SPF to Thailand. 2004. This is a 15-day-old animal in the pond. Good success, but that wasn't enough. We started selecting, and today, at 15 days, they look like this. So we still have healthy shrimp that now grow fast, and that fast growth is basically key to keeping your cost low. But they have to live. If they die, who cares? Next. So again, I didn't read the little bottom there, but to get them to live just like they did in 2002, you need biosecurity. Our SPF animals in 2002 would die of white spot. But in Asia, we concentrate on small controlled ponds with biosecurity. So let's go through a process, because everybody says biosecurity. Nobody understands biosecurity. I've always said to have biosecurity, you have to know your enemy. We knew white spot, but we didn't know aphids and we don't know EHP. Know your enemy, and then you can create biosecurity. So, the enemy. If it dies, that's aphids. If it dies with birds, meaning they get sick, that's white spot. And if we have slow growth and high size variation, that's EHP. I learned an interesting term at the DSM meeting. It was called symptomic surveillance. So that's what I do. If I go to a farm and it's that, aphids, white spot, and microsporidium, I look at the picture and I have my diagnosis. Next. And then we need to understand. So, to create effective biosecurity, I have to understand aphids, I have to understand EHP, and I need to understand white spot. This for me is EMS. 3 diseases. Yeah, I know they don't all die early, but for me, today's issues are 3. You have to have all of them. And then we need to select genetic stocks of shrimp for the 3. And that takes some time, but it can be done. Next. So, the 3 new rules of biosecurity in the new age of EMS. Now, there's a lot of solutions, and I'm not smart enough to come up with the best ones. So, I come up with general principles, and I let you come up with the best solutions. You just have to make sure you follow the principles. White spot. Okay, we know the white spot routine. Biosecurity for white spot, you got the birds, you got the water, you got clean PLs, you got to keep the crabs out, We all know that one. Aphids. It's not about exclusion of the bacteria. You can't. Don't even try. It's about reducing the bacterial food and the substrates to keep the bacterial level low. And then EHP. Biosecurity rule for EHP, clean broodstock, clean PLs, clean farm, and clean water source. I call it the 4 C's. If you got those, you don't have EHP. Next. So, we always start with clean, healthy, SPF post-larva. This is no. Okay, if your HP tubules look like this, you've got a problem that you don't want to be stocking because this type of animal is going to be sensitive to disease. This is, yes, healthy, active, low CV, low size variation, healthy HP tubules. Always start with a healthy PL. Next. Okay, I'm not going to go through the white spot exclusion, biosecurity. We all know this. I think I first showed this one in 2003. So, we know this one. Next. But we need to understand aphids so we understand why we create the biosecurity that we do. We must have threshold numbers of bacteria because of this thing called quorum sensing. You have a few bacteria that matter. They don't produce toxin. We need a certain number of bacteria to hit a threshold to produce toxin. Then we need to understand aphids bacteria grow and produce toxin on the following. Shrimp feed. If your shrimp food is in the pond too long, that's going to become a very high level of aphids and it will kill shrimp. Shrimp shells, molts. Aphids loves molts. They love chitin. And shrimp like to eat molts. That's a problem. And shrimp sludge. Basically, that's partially digested shrimp feed. So yes, aphids likes that too. And the problem with Van Amme likes all of this. They'll eat old feed. They will eat sludge. They will eat molts. Van Amme is a non-discriminatory eater. So it eats the toxin. And then finally, shrimp must ingest the toxin from the environment. If they don't ingest toxin, they don't die. So, that's really all we need to know today for aphids. With that, you can go out and create some wonderful management. Next, understanding EHP. EHP is a parasite, kind of like a virus, you need the host, but in this case, it's a fungus. So we kind of know that. Exclusion is kind of important here. It's like a virus. And EHP survives as a spore outside of a host for a very long time and is difficult to disinfect. That makes it more difficult than a virus. If a white spot viron is outside of the host, it's gone in 3 days. If an EHP spore is outside of the host, it stays around a long time. So, as it requires a host, and the only host we know at this time is another shrimp, exclusionary principles will apply. Clean broodstock, clean PLs, clean ponds, and then clean water that you use on the farm or the hatchery. All right, next. So, now usually I do the EHP last, but they say EHP is more important, and when I get to the end, I run out of time, so we never do EHP. So today I'm going to do EHP, and if we run out of time, we won't do aphids. And I won't even attempt to say this. EHP. I used to say EH, but then George says it has to be EHP to rhyme with EMS. Okay? So we'll call it EHP. I can deal with that. And you can see it under a wet squash in the HP. This is under basically 100x oil immersion. If you have really good eyes and you've learned what to look for, you can squash it and see the EHP spores in a wet mount. Next. Now, we've had microsporidium before. Usually we called it cotton shrimp, and it required an intermediary host. It required a carnivorous fish. So this microsporidium is different. It doesn't require an intermediary host that we know of. It has a much higher prevalence. Usually we'll only find this at 3 or 4% in a pond, whereas EHP will have almost 100% prevalence. And this is in the muscle tissue, and EHP is in the HP tissue. Next. Characteristics of EHP. For me, this is as good as any PCR. When an Asian shrimp starts growing slow to less than 0.15, I will almost be 95% sure we have EHP if it's an Asian population of shrimp. We will usually see if it's a higher density, we'll see a spread in size uniformity. And if it gets really serious, and we're measuring with our fine real-time PCR, we get above 10.6, 10.7, we'll sometimes see loose shells. Okay, next. Detection can be difficult, and this is the reason that EHP is the problem it is today. It spreads through the rootstock, it spreads through the PLs, and detection is difficult. You really need a real-time PCR to get down levels that are important for carriers. If we use your normal PCR, you need above 10 to the 3 micrograms of DNA. Okay, that's almost a symptomatic stage. It's at a disease. But there's a lot of shrimp out there that are non-symptomatic, that are carriers, that are below 10 to the 3. So your PCR shows a negative when in fact they're positive. Now if I'm using real time, I can get down below 10 to the 1. All right, that's better, but it's not perfect. If we're using histology, I can tell you, I have sent samples to the best pathologists in the world, and they missed it. They missed it more than once. Because under HE stain, you can't see it. Very difficult. Now, if we use in situ hybridization, it lights up. But under normal histological conditions, unless the pathologist really is looking for it, he will miss it. So we're missing it with PCR, we're missing it with histology. And now we're sending broodstock everywhere. Next. Spore destruction is difficult. Not impossible. Please, journalists, take note, not impossible. I got in trouble because it came across as it's impossible. It's only difficult. If you don't find destruction with defecation or sun drying. There are reports of microsporidium spores lasting 50 to 60 years in a dry state. Probably not good for farm management. I know from experience that chlorine at 200 ppm is not necessarily effective. I know from experience that ozone is not necessarily effective. There is some confusion about freezing. Some people tell me freezing yes, some people tell me freezing no. It may be we just haven't defined freezing well enough yet. And if this meeting was maybe a week from now, I would answer the question. Next. So, what are some of the outward signs? Well, one of the confusing things is what we're calling this white sheet, these white things. A lot of people think that that's symptomatic of this. I used to think that. I'm not so sure anymore because I see shrimp now all over the world with white things, and I don't think they have EHP. But certainly when you do have EHP, these white sheets are very common. Next. And you can see it in PLs. In fact, this thing will infect in the hatchery in PLs. It can get very badly infected in the hatchery if you got a bad infection. And then you can also see the little white things in infected PLs. That's a pretty good scientific term, little white thing. Don't quote me. Okay? Next. And then white feces. Is that or is that not microsporidium? All right. Again, we have some divergence of opinion. My opinion is it is. Others, it is not. I have my opinion because I've never seen white feces that did not test positive for EHP. Now, I have seen EHP not produce white feces, but I'll tell you one story. I had an intensive tank, lots and lots of shrimp. They were wide size variation, growing slow. They had EHP, no white feces. Then I had a biofilter failure. I had a spike of nitrite. The next day I had white feces. And we know white feces are associated with bad bottoms. So I think when you have EHP and a bad bottom, you have the conditions to create a super condition of white feces. Opinion, no scientific evidence. Observational. Next. And the other thing that I first noticed, now EHP is not new. Okay, we first saw EHP in Thailand in 2009. And it took us really about until 2010-11 to figure it out enough that we cut it off. So today, you find some EHP in Thailand, but not very much. Now, one of the things I noticed when we started seeing HP, actually I didn't, David Garrigas that works for me did, he saw these worms in the HP that he had never seen before. And they looked like gregarines. Oh, we showed all these to again, the famous pathologists. Some of them immediately were astute enough to say, there's no nuclei, it can't be a gregarine. Others would just say, well, we can't see the nuclei, it must be. So we actually took money and you can pick these worms out of the HP. So you can pick a tube full of these things. And we sent it off for genomic analysis, and it came back shrimp. Did that 3 times before we were convinced it really was the shrimp and not some foreign body. I do believe that when you see this, there are or there's the microsporidium involved in the production of these tubules within the HP. So that is one indicator I look for. If I have this in an HP, I'm pretty sure I have microsporidium. Next. EHP directly affects horizontal vertical transmission. Okay, in the hatchery, if your brood animal is infected, it basically will infect the nuclei we always have that fecal to nuclei transmission. It is a fecal to nuclei transmission, so we can infect to the nuclei, then go to the PL, and then go to your farm. Or if you're in the farm, and somehow we just get 1 or 2 infected individuals, we can get horizontal transmission through the water. So actually in an experimental condition, I can take an aquarium, I can half it, I can put infected animals here, clean animals here, and in 4 or 5 days, the clean animals are infected through waterborne transmission. It can transmit through spores in a pond. Now this is another rule that I have. If your pond has been infected, it's infected forever until you do something. The spores are in your pond, likewise in your hatchery. Wherever this thing goes, you can be sure they've left a present in the form of spores. And unless you take action to destroy the spores, it will be a continuing, if not accelerating problem. Next. Carriers of microsporidiums, well, again, pond-reared broodstock. It's not nuclear breeding. They're exposed. They can carry it. Broodstock feeds. We've seen it in polychaetes, in bivalves. Now, this is passive, okay? Passive means these things are in infected areas, picking it up, and it's passing through their intestinal tract. But it can still infect. Nuclei, infected maturation. PLs from infected nuclei, pond reservoir bottoms. I made this mistake before. I had a problem on a farm. I disinfected the whole farm, and the next cycle I had the problem again. I missed the reservoir. It's in the reservoirs too. You got to disinfect everything. And source water. When you get a neighborhood where everybody's got the disease and everybody's passing the spores into the local water, yeah, it's there too. And now it's going to come back and bite you again. Next. To prevent EHP, we must be clean. Now, this may be pretty simple, but sometimes it may be difficult because in a lot of cases, this requires cooperation. Everybody needs to be clean, otherwise the environment gets dirty. We have to start with the clean broodstock, then go to the clean PLs, then go to the clean farm that has clean water. The whole line of possession has to be clean. Okay, next. To disinfect. Okay, I said it was difficult. It's not impossible. There's ways of disinfecting anything that you come up with. Now, in this case, we're looking at pH because the microsporidium is a chitin wall. Fungus have chitin, and chitin dissolves at high pH. So we can actually dissolve the chitin spore wall, and that destroys it. So here we basically add calcium oxide, which can get your pH very high. Now I must add caution. When you use calcium oxide, this is the same chemical the mafia uses to get rid of evidence. They basically dissolve bodies in this. So you need to make sure your workers understand that if they dip their hand in the calcium oxide, it'll come out a bone. Must be careful. You plow it into the sediment, and then you have to moisten it. We need the reaction. So you need to react it. Get the pH above 12, and then within 1 week that pH is going to correct again. It's going to come down to levels that you can stop, but without the spores. Next. Now another thing that we learned, or I learned maybe 3 or 4 years ago on a farm I had, that we always wondered why. Okay, here, this is complicated, and probably if I did this again, I probably should do it easier so that even I can understand it. But this is a non-infected PL. So this is one farm. Some ponds got infected PLs, some ponds got non-infected PLs. So the non-infected has a normal growth curve. The ones that are infected basically had a normal growth curve to 30 days. And then it slows down. So it's normal to 30 days before it goes. Now why is that? So we set up a program with a real-time PCR to look at DNA amount, which is proportionate to spores, to see if there is a relationship with the concentration of the spore in the HP and its effect on growth or health of the shrimp. And basically we found that below 10 to the 4 levels, there's no effect. There's no disease below 10 to the 4. But as the days go on in the pond, the spore numbers increase, and when the spore numbers increase above 10 to the 4, it starts growing slow. And then if you happen to keep that animal in the pond in 90 days, you'll oftentimes reach 10 to the 9 or 10 to the 8 DNA units. Now at that point, you can actually see some chronic mortality. But most people don't keep it till 90 days. So generally we don't see chronic mortality, we just see slow growth and increasing size variation. Next. Now this is an EMS environment. You don't get one disease or the other. You get both. Most shrimp today we can find Apin's DNA in the stomach, and we can find spores. So it's not, oh, I'm going to have this disease or that disease. They're all mixed in. And also, there's probably some white spot. I just didn't measure that. We're in an EMS environment. Now, the combination of this is kind of interesting. I really don't have anything definitive today, but I think from an observational point of view, it asks some interesting questions. Before EHP got spread all over China, all over Vietnam, all over India, forget India, China, Vietnam, Malaysia, EMS, Apin's killed. Now there seems to be a switch to a bigger problem of EHP. But we don't see the early mortality any longer. It's just slow growth. Is there an interesting interaction here? Question to ponder. Next. Are we falling asleep? Haven't started Apin check, you know. Now another observation, and again these observations I made in India, I made in Vietnam, and I made in Thailand, is that if this no infection, my shrimp is going to grow to 28 grams, but as my salinity increases from 0, I get almost no reduction in growth at low salinities. But as they increase, I get a higher effect of the microsporidium. So when I'm in India, even if they're stocking low density at 40 or 50 parts per thousand, very high impact. But if I'm in Thailand and they're stocking 60 and they're at 0, I see almost no impact. So this needs to be confirmed through experimentation. Same way with density. Lower density, less impact. Higher density, higher impact. Next. Management. Okay, this is basically what we've just gone through. Start with clean animals. Then you disinfect your pond if you had the disease in there before. Your reservoir, you make sure you get rid of the spores. Now, if it were my farm, I'm not so sure of my own skill. So I'm going to lower my stocking density. So even if I have a few spores left, these animals are going to grow up to 25, 30, 35 grams, and I'll still get a profitable crop. And if I don't get an EHP, then the second crop I go back normal. But at least I hedge with a slightly lower stocking density. And then, again, if you have the option for lower salinity, it's certainly better than high salinity. All right, next. Do we have time to continue? Okay. Aphids. Understanding aphids. The first thing that I will say, and I understand that most people in Malaysia already understand this, aphids is not a vibriosis. It's not a systemic vibriosis. Now, how do I know that? Very simple. If I take a large amount of aphids bacteria and I heat kill it, and then I feed the heat killed bacteria to my shrimp, I still get aphids. The histology is there. The disease is there, even with a heat-killed bacteria. But if I take a heat-killed Harveyi and try to infect a shrimp, nothing happens. That's vibriosis. You need a live animal. This, you need a toxin. Whether it's dead or not, the toxin is there. This is a toxicosis. Next. So, a typical aphids challenge. This is, again, just verification of what I said. If I add the aphids here on day 2, so I get my shrimp acclimated a little bit, I add day 2, wow, rapid death. There's no sickness here. They're alive and dead. And this is the first thing I observed in China in 2009, where I said to myself, this is something different. I would go to ponds, and there would be no sick shrimp. There would be dead shrimp and healthy shrimp. So, very fast. Now, oftentimes you'll look at these challenges, and we'll start seeing dribbling mortality after that. That's from secondary bacterial infections. The survivors sometimes get stressed enough to pick up a secondary bacteria, and that creates the chronic phase. But it's not the primary toxin. That's within 12 hours. It dies. That's another thing that you will find. In a live shrimp, you will never find aphids systemically. You'll never find it in the HP. You'll never find it in the blood. You will only find it in the HP in the blood when that shrimp is next to dead or dead. Next. This is hopefully to illustrate the toxicosis. But essentially, it's like having a cockroach. Imagine this being your shrimp, and we spray the aphids toxin on it, and it's dead. Toxicosis. And in fact, the Peter toxin 1 and 2 are natural insecticides. It really is like spraying your shrimp or your cockroach and killing it. Next. Okay. Initially we called it early mortality because in China and other places I saw it before 30 days. But in fact, it can occur at any size. At any size, the shrimp ingests enough toxin to kill it. Now, a small shrimp requires less toxin. A big shrimp requires more toxin. Okay, next. The toxin is produced in the Vibrio, and therefore the ecology of the Vibrio does matter. All right, we always want to talk about infections of the shrimp. You know, for 3 years I talked about infections of the environment, and everybody got angry with me and said didn't know what I'm talking about. I'm still talking about infections of the environment. So, Fuji in China 2010, this represents all the CPPL sales. So I have a good record of failures. Basically, failure rates go up when the temperatures get hot. And when the temperatures get lower, failure rates go down. Experimentally, I can show more toxin and more growth of the bacteria with temperature effects. This is the real world. Same way with salinity. If I look at Thailand, different salinity regimes, basically where we have low salinity, we have low failures, and where we have high salinity, we have high failures. So this is plus 30, and this blue is 0 to 10, almost no failures at low salinity. Experimentally, can also show the same thing. If I challenge at low salinity or grow the bacteria at low salinity, they don't grow very well. In fact, they don't grow at all below 4 or 5 ppt. Next. Aphids is about the environment. Low diversity encourages aphids. Now this is a picture from a Chinese pond that's ready to stock. I think this was probably 2010. If chlorine and killing everything prevented aphids, would China be dead? Would Vietnam be dead? Would all the farms in Thailand that use chlorine be dead? Chlorine was not an answer for aphids. If it was, we wouldn't have a problem today. High diversity discourages aphids. Aphids, if we want to get ecological, it's an opportunistic bacteria. It goes in where other things are not. It's not very competitive. If I create a very competitive environment, aphids has a hard time to grow. So, rule, low diversity, encouraging. High diversity, discouraging. Okay, next. Aphids thrives in low diversity, opportunistic environments. This is 2010. Okay, maybe this was Vietnam, not China. Lots of blue-green algae. Blue-green are another opportunistic organism. Now, when I started seeing this in 2010 in China and Vietnam, I'm thinking to myself, I remember growing up in shrimp farming, and we had diatoms and we had greens. I never saw blue-greens before in any large amount, but in China and Vietnam, it was all blue-green. We lost the greens, we lost the diatoms. Why? I didn't know at the time, and that's why initially my first hypothesis, this was aphids. Filamentous blue-greens that I found everywhere in China and Vietnam. And later, when it hit Thailand, the filamentous blue-green came along with it. If we look at the zooplankton, we find rotifers now. The copepods are gone. Copepods are your mature organism, and rotifers are your opportunistic organism. We have created pond environments full of opportunists, when in fact we need to be encouraging the mature organisms that don't allow opportunists into the environment. Next. Okay, now I started, and I'm doing my presentation. I sit at my desk and I said, what questions would I want to answer? You may not want the answer to these questions, so come up with your own questions. But what is the agent? I think we all know the agent. It's a natural insecticide. It's in a plasmid. It's in a Vibrio carrier. The Vibrio is a carrier of the plasmid producing a natural insecticide. And yes, now that I know where to look, I can find aphid strains everywhere. I just go to a pond, I scrape out the stomach, the chitin area of the stomach, and I come up with a new strain of aphids. All strains, though, have the plasmid and the natural insecticide. Next. Histology has more than one lesion type. Now this has caused a problem because this is the definitive defining lesion. It only has a lifetime of a couple of hours in the shrimp. It's transitory. And so if you don't do a lot of shrimp, you will find one of these lesions and come up with a diagnosis, serious vibriosis. Okay, so there's a lot of lesions that Apens is responsible for, but the defined lesion is really very transitory. You have to look at a lot of shrimp with a commitment to finding it. Next. How to test for Apens. Now, again, we're dealing with a PCR, so we need a certain amount of DNA. And when you have a low amount of Apens in the stomach or on the chitin or wherever you're testing, you get PCR negative. If you want, and this has been the problem in places in the Americas and other places where they keep telling you, oh, we don't find it, we don't find it, we don't find it. You got to amplify it. And when you start amplifying, oh, you find it in a lot of places. So we have to amplify it, enrich it. And so, if I go to a place, I will take the head or the stomach and I'll put it in enrichment medium. I'll leave it there sometimes for 2 days before I PCR it. And you'll be surprised how much more Apens we find. Okay, next. How does it move? Well, in the beginning, it was just our normal routes. This is somewhat still speculative, but I believe it moves in, of course, rootstock, post-larvae, frozen shrimp. Yes, you can revive it from a frozen shrimp. You get non-culturable forms in frozen shrimp, but if you give it time, it comes back to life. Maturation feeds, zooplankton in the coastal waters. Yes, I can go off the coastal waters with my plankton net. I can collect zooplankton, and it will test positive. Birds, not sure about this one because, again, the pH of the stomach is such that it may destroy it, but we certainly can get PCR positives out of bird feces. And the air, I put a question because I was pretty sure it would move through the air, but I have looked. I have concentrated air for days and days and days, and I haven't been able to find it in the air. I'm not convinced it's not there, but I haven't been able to find it. Next. Can the agent be excluded? Now this is my favorite picture because it's so beautiful of biosecurity old style. This is for white spot. And it was very, very good with white spot. But Apens, this doesn't work. You can put up the best biosecurity with Apens, it's not going to leave the system. So, answer no. We have to come up with other ways of dealing with this. Next. Okay, questions on the ecology, physiology. All right, we already went over a lot of that. Where is the toxin? It's in the environment. Yes, I can find the bacteria attached to the stomach of shrimp, but it's on all the shrimp. Whether they're dead, healthy, or alive, I can find Apens in the Apens environment on just about all the stomachs. That doesn't seem to be the answer. What are the factors? Okay, I spent 2 years doing factor after factor, everything I could think of. Factor, salinity, temperature, nutrients, trace minerals, pH, every ecological microbial factor I basically tested with Apens to see what factors are important. And overwhelming, the factor that's important is food. You've got to control the food of the bacteria. And then what are the factors that produce toxin? Factors that grow the bacteria and factors that produce toxin can be different. So there's some factors that are important in growing bacteria biomass, and there's other factors important in creating higher toxin levels. Separate conditions. Next. So I have a whole bunch of stuff, but I took them all out because I'd be here for hours. But I put what I consider some of the more interesting ones in. Accumulation of toxin in leftover feed. So I created an artificial environment where I just put a little bit of Apens, 10 to the 1 bacteria. 10 to the 1 do nothing for anything. And then I put the pellets in there for different hours, And the longer time the pellet is in this level of 10 to the 1 apens, the more it killed, the higher the toxin level. And now I can take these pellets out and actually test them with ELISA and quantify the toxin at different hours. What this tells you is when I feed a pond, if that feed is left over and the shrimp eats that leftover feed, you're putting the shrimp at high risk, especially if there's aphids in the environment. Now, I take this and I use real time. I've got ELISA now. Real time was all I had when I did this. So then I look at the DNA count, proportionate, and as the time goes up, the real-time copies go up of aphids on the feed, and then this is proportionate to how fast they die. This basically created the whole new mindset for me of really the key to solving aphids. The other thing is, Van Emme will eat old pellets. I remember in the Americas, we used to feed one time a day. Throw out a whole bunch of pellets in the middle of the pond, and the shrimp would nibble on it all day long. Van Emme don't care. Now, Monodon care. They won't eat bad food. Van Emme, they eat anything. Next. So, important question, what is biosecurity? I've already told you it's not exclusion, but limitation or control of the pathogen numbers. Now, the proof of that is what we call quorum sensing. If I challenge at different levels of bacteria, I really have to go over 10 to the 4 to create a response. At low levels of bacteria, we don't really get a toxin response. So all I have to do is control the numbers. I don't have to be absolute exclusionary. Next. Now this gets too complicated, but I'll give it a try. High dose. This is from the environment, okay? If it starts sloughing like this, recovery, I say unlikely here, it ain't gonna happen. It's gonna die. But if it's from the stomach and it gets a low dose, now stomach, if I go into a pond, I get all these readings, the real-time readings from the stomach, and the shrimp are like this, they're totally healthy. But every shrimp has relatively pretty good numbers of aphids in it. But it's not enough toxin to create this. This has got to come from the environment, ingestion. This, basically every stomach that you go into a pond, healthy or not, you're going to find some aphids. Okay, next. How are we going to do this? We're not creating any size yet. Next. Now, I was in South America, and I won't tell you which country because they're not supposed to have it. But one country showed me their data, and they had mortality peaks. And they go, why do you think we're getting these peaks in mortality? Well, these peaks in mortality corresponded with an event. High molting activity. The molts carry the aphids. And when you have that high molting activity, you can actually pick up higher incidences of mortality. Next. What does tolerance mean, and is it genetic? $1 million question. This is Monodon. Probably recognize it because I still understand Malaysia likes Monodon. And I understand that Malaysia actually gets pretty good results with Monodon, when in fact in some places Van Emme had not done well. So, is this tolerant? Is this genetically tolerant to aphids? So I ask that question. I take this into my challenge center, and I challenge it with an equal amount of toxin or aphids under the same conditions as I do Van Emme, and guess which one dies more? This one. This one is a lot more sensitive to aphids toxin. But in the pond, it doesn't seem to die. Now how can that be? Well, I've come up with a term, don't know if it's real or not, but it's my term, behavioral tolerance. means it avoids the toxin in the environment. Monodon loves fresh stuff. They don't like garbage. They don't like sludge. They don't like old feed. They don't like the places you find the aphids toxin. And so they don't die. If Monodon die, it'll be in the first 30 days, usually as a result of poor quality PLs from the hatchery. But if you get past 30 days, Monodon's good to go. Behavioral tolerance, not genetic. Well, maybe that's genetic. They don't like bad food. Next, real genetic tolerance. Is there such a thing? The answer is yes. And it's really interesting, after this DSO conference, I think in the food safety session, somebody said something about something, and I couldn't sleep the next night, and I started Googling things. And I learned a lot more about tolerance than I ever knew before. There's a lot of good insect models on tolerance. And so, tolerance and resistance are very different. And we can create tolerance. And we are creating tolerance. And yes, it's even heritable. Before you can use the term genetic, you must show heritability, in my opinion. This is basically a phenotypic response over 1, 2, 3, 4 generations. And we can see a phenotypic response to tolerance development of the toxin. I'm not looking at this as a vibriosis. I'm looking at this as a toxicosis. I want real tolerance to the toxin. And again, I look at here, this is like one batch of families. I've given you the genetic talk before. We run like 3,000 families a year. Yes, some families have very low tolerance. Other families have higher tolerance. The question is, can you select it? The answer is yes, you can. The heritability is moderate, so it will take time if we're just looking at a selection on a family basis of the characteristic. But it's an important thing. It is heritable. And we recognize that, I think 3 years ago. For 3 years we've been working on this. So next. So, a lot of talk in the blogs. I lost my mojo because I read too many blogs. It really can get your confidence down. Oh, you grow fast, you're going to die fast. Yeah, that was my nickname. Die fast, grow fast. But this shows our growth improvement from our beginning. This is where I started selection for aphids tolerance. So you can see I moved the index, and the growth improvements slowed down as I started shifting to aphids, but it didn't disappear. And when I run correlations, in this case I run TSV and raceway growth, you see a positive relationship. I can improve both at the same time. I have the same correlation for aphids, I have the same correlation for white spot. It's just I had more data points, it looks nicer for TSV. But you get the same correlation. You can improve growth, and you can improve tolerance. They are not independent. Okay, next. And we run it with pedigrees. This allows more precision in what we do. It allows precision in knowing the characteristics of all of the fraternity. So every single founder, I now know every single parent, I know everything there is to know about our whole population from the very beginning. And on top of that, I have tissue samples for every single family in the program. You know what that means? That means in very short order, we'll have a complete genomic analysis capability of relating genomics to disease tolerance, to growth, to fecundity, and our breeding will even become more precise. Next. The program, maybe it's luck, but was a little bit better designed than that. Okay, next. Important question, how do I maintain the low aphids levels in the pond? Okay, that's $1 million, maybe that's the second $1 million question. how do I keep the aphids levels low? Well, something that I saw, again, early on, maybe it was 2010, driving along Hainan Island, and we stopped at this one farm, and he had 2 lines of ponds. One line was looking at the South China Sea, and it was getting sea intake. The other line was right next door, but it was getting well water. This was 100% successful, and this was 100% failure. Since that time, I've seen the same thing in Vietnam. I've seen the same thing in Thailand. When we're using groundwater, there seems to be a much lower incidence of aphids. I could not figure that out. How can that be? How does that fit into our hypothesis? Well, again, I do believe now that the groundwater just has lower levels of aphids. There's no zooplankton bringing in aphids here. So we're starting at a very low level, and it takes longer period to build up. So start with a low level of aphids. Here is a farm in Vietnam, again, using the same idea. He's on the beach, so he puts in a deep sand well, he brings in, and this has also been a very successful farm in Vietnam, using beachhead filtered water. Okay, next. Don't feed the aphids bacteria. Now this was, honestly, people, when I came here, people started talking about flock. I came from Belize, we use flock, and somehow it got conceptualized that to have flock you need molasses. I never used molasses in Belize. You don't need molasses to grow flock. But what molasses does grow is aphids. You can prove it. Take yourself an aquarium, put molasses in it, put your shrimp, put some aphids, they'll die. Don't put the molasses, they won't die. The molasses grows aphids. Now let's look at that theoretically. Aphids is a green TCBS. Green TCBS use monosaccharides. They don't use di or polysaccharides. So in our thinking, we're going, molasses is sucrose. Aphids won't eat it. No, molasses, if you look at Wikipedia, that's where I get most of my information, Wikipedia. I think there's 20-25% glucose fructose in molasses. It's not full sucrose. It is a byproduct of sucrose production. So when we're dumping a lot of probiotics with molasses in the pond, and I can show you real instances, if we had time, of ponds and farms that did this, and they failed and failed and failed, and they stopped failing. Don't feed. Now, I got really smart 6 months ago and decided, let's use sucrose in the feed, and that will allow the yellows to colonize and keep the greens off, because I knew the feed was a problem. So I'm going to put, brilliant idea, I'm going to put sucrose on the feed, but I forgot my chemistry. Sucrose is basically 2 glucose molecules that when you put them in a complex biochemical reactor like a pond, and hydrolyze the glucose times 2. I killed off 2 ponds real fast. Faster than I ever killed a pond before. Because my brilliance forgot the hydrolysis reaction. Next. Encourage environmental diversity and complexity. So when we run challenges, what I call mature water, that's water that I don't chlorinate, that I just add different stuff to and get more, and you can see the different complexities of the bacterial communities. If I had chlorine water, there'd only be like 3 or 4 bacteria down here. But with tilapia water, or flock water, or mature water, where we're dealing with more complex communities, it's all positive for aphids control. Doesn't matter. Some people say flock, some people say tilapia, mature. You just need complex ecosystems. Next. Okay, demonstrated complex water use aphids. Here's my tilapia picture. Yes, you get some of the complex bacteria out of here, and they actually have some aphids killing abilities. This is just one of many, but it's really about the complexity and not allowing an opportunist like Vibrio parahemolyticus to become dominant. Next. 4, quickly eliminate all substrates that apis grows on and shrimp consume. Okay, coming at the bottom now. Uneaten feed, shrimp molts, sludge, foam from dying algae blooms, all great collection points for apis bacteria. So, how is this possible? I think this is one of the most fantastic inventions of all time. Next, the shrimp toilet. Okay, this is a must for every shrimp farmer in Southeast Asia, if not the world today. With the properly installed toilet and flushing device, you can reduce the level of aphids to the point it's no longer a problem. The shrimp toilet. Basically, what's the cost? I don't know. How long does it take you to go out there and dig a hole? Okay, next. Okay, so you can have toilets in earthen ponds. We don't need to line ponds. You can have earthen ponds. You can put a toilet in an earthen pond. This works. Grow shrimp. Next. We can put it in a line pond. This works. You grow shrimp. Next. And then you got to flush it. So, when you start building up the biomass as we build up, every 10 minutes or every hour they'll be flushed 10 minutes, and you'll get this coming out, and you need to wait until it gets clear. Now your bottom's clean. Next. We're removing the molds. Now, some farmers are so considerate, they capture the molds that come out of the toilet because they don't want to infect the water. Well, I think that's good. But what this shows you is how much molds are being collected from the toilet in real time, not allowing the shrimp time to eat them. Next. And there's a trend of making large ponds into smaller ponds, because smaller ponds are easier to control, easier to keep the bottom clean. But I showed you that second slide, that was a 1 hectare pond that was kept clean enough to get 30 tons of 50-gram shrimp out. So it doesn't have to be super small, but again, a lot of people are going smaller from larger because it is easier. And I can tell you, from my own experience, if I got a choice of small or big, I'll go with smaller. But if I don't have a chance to cut it down, if I got a 1 hectare pond, I can make it work. Next. The amount of water you need to flush. This is some areas that we're still working on, and there's a lot of improvement. You can come up with better ways. Now in this scheme, we're using a reservoir that is 50% of the culture area. I think we can get better than that. I think we can get down to maybe 30% reservoir and 60 or 70%. But today, this would be a common configuration with a lot of water to flush the ponds. Okay, next. And then, as a final reminder, or a final note, don't put the flush in the environment. This is nasty stuff. Create a settling or a sludge pond. Now in this case, this is a very deep pond. And they put tilapia. Now those tilapia actually recycle a lot of the waste. They keep your sludge pond a lot cleaner. You don't have to regenerate it so often. So in this case, the flush goes here, and then there's an overflow to another reservoir where the water overflows, also with fish, and then this recycled water is used to flush. So in this case, it's a completely recycled system. But in any case, when you're flushing, don't flush to the environment. This is really bad stuff and will lead to our next episode of chaos in the industry. Next. So, I'm going to end. A new age of Asian shrimp farming has begun. The mojo is back in Thailand. The mojo can return here. It doesn't have to be complicated. It doesn't have to be super expensive. You just need to follow some principles and new rules of biosecurity, and we can get back. We must change. We changed in 2003 in Thailand. We were failing, we changed, we came back. Today is another day of change. We need to change, adapt to the new situation, And it's not that we will come back, we are back. It's getting better. And so, I just want to live with my CPF logo, because I've been bashed so much for it. Proud to be SPF? Yes. And proud to grow fast? Yes. Thank you.
For the very enlightening presentation. First of questions. I think there are some shrimp feed, right? Yeah, not nutrition feed, but not live feed, but processed feed, both for the farm as well as for hatchery use has been tested positive AHP.
Yes, it has.
Yes, how did they come about? And are they usable?
Bad primers.
To use? And,
Bad primers. You know that there's krill out there from Antarctica that's positive? Krill, a tropical microsporidium in Antarctic krill. So, I'll tell you a story. It's not a story I'm proud of. But my staff came to me, maybe it was a year and a half ago. Oh, our broodstock raceways are positive. Tested the feces. I go, oh, test them again. Positive. $1 million worth of broodstock. Positive. I immediately made the correct decision, destroy them all. Clean it. And so, $1 million of broodstock destroyed. Then I got one of my, again at midnight one night, I'm thinking, wait a minute, what if it's just in the intestine? What if it's not infected? Because how can a processed feed be infective? I remember my white spot days. You know, the heads were white spot positive, went through the pressing, and the shrimp, the intestine was still positive, but they never infected. So I told them to go back, go and test the HP, and they were negative, no infection. And then I'm going, how did this happen? I only feed pellets. I try to do the good job on broodstock. Only feed processed high temperature pellets, no live feed in the broodstock. How did this happen? So I tested the feed. Positive. Whoa. The feed is positive, but it's not infective. Then we started testing fish meal, krill meal, all kind of things. Positive. Whoa. How could this be? Well, it seems that the primer we've been using was somewhat generic. It was close, but it was generic, and there's a lot of microsporidium. I think Wikipedia tells me there's 100,000 microsporidium out there. So now, today, and I don't know if it's been published yet or it's on the web yet, but Tim Flagel, I furnished him a whole bunch of shrimp, and he purified the spores from this one. We got it genomically validated, and he came up with a new primer on the cell wall. Now that's specific. That primer I don't think is going to give you a positive on the feed, and if it is positive on the feed, that feed is non-infective. That answer? Thumbs up.
Okay, we have one more paper to be presented by Mr. Louis Wong. Okay, he will talk about the latest technology that are being used in
this morning. I think he's essentially covered this entire topic very well. So we will be able to go through this much faster because I think we'll just skip through quite a few slides that have already been covered. So let's begin. So next slide. So here's what we plan to cover. A little bit about EMS, the pathogen, the management, and mainly we want to get down to the results here in Malaysia with the trial. So we'll share some of those results at Blue Archipelago, where IAQUA and Blue Archipelago are working together. And then we'll talk about EHP And I'm afraid there it's a little bit more theoretical because EHP just hit the farms in Malaysia in a significant way this year. So we don't really have much in the way of actual production results yet from the things we're trying. And then I'll talk to you a little bit about developing the biosecurity plan and the steps involved and what that process involves. Okay, next slide. Mr. Bakar.
Thank you, George. We've seen this data many times already this morning, and this is the set of data that we think from our own surveys. Untuk pengetahuan semua ya, kita dah lihat data ni beberapa kali pada pagi tadi. Memang beberapa menunjukkan data yang sama, iaitu apabila EMS melanda negara kita tahun 2010-2011 ya, daripada setinggi 90,000 tan, dan sekarang mungkin 2015 anggaran kami ialah mungkin hanya 30,000 tan ya, jadi penurunan ya, yang disebabkan oleh EMS adalah ketara keadaannya. Jadi saya memang kalau saya tengokkan ladang kami di Blok Teleko, di Situ dan di Kerepan, memang Kerepan telah dilanda dengan penyakit EMS, dan terpaksalah kami bertukus lumus untuk bekerja untuk mencari penyelesaian. Itu sebabnya kita ada satu kerjasama di antara pihak IAQA dengan Blok Teleko, dan beberapa kajian dan beberapa inisiatif yang telah kita buat yang kita ingin berfungsi sama dengan semua dia punya kajian yang telah dijalankan. Jadi ini yang George akan berikan penerangan sekejap lagi ya.
Next. So I think we can skip through this pretty quickly because Robin's already gave us a great review about the EMS pathogen. And the key thing is that once it's established in an environment, it's very difficult to get rid of it. It grows very fast in the presence of nutrients. It attaches to detritus, and it, like most Vibrios, it doesn't survive prolonged freezing. Now that may not be 1,000% true, but in general, Vibrios are known not to be resistant to freezing. Next slide, please. I think we can skip over this, the growth signs. I think we're all familiar with those and what a sick shrimp looks like. Next slide. Robin's covered this as well, the vertical transmission. It's super important that we understand that the disease can be spread from the female to the egg, mainly from the fecal contamination. So when a female spawns, all of the contents of her intestine also end up in the spawning water. And so the EMS pathogen can be there and it can end up infecting the next generation. And the key culprit in this whole process is live worms. Everywhere in Asia, every hatchery wants to use live worms, almost 100% live worms, because it increases the nuclei production. But to get the live worms locally and they're infected, and that's the #1 hazard if we want to go to a biosecurity plan. That's one of the critical control points, not to use live feeds in the hatchery. Next slide, please. So on the horizontal transmission, I think the key thing that's come out of some research in Mexico, and Robbins, I think, has done some of the research too, is that below a threshold density, there is no toxicity. And 10 to the 4th colony forming units per milliliter is considered the threshold density. And that's really, really important. That means we don't have to totally get rid of EMS, just keep the density below that threshold level where toxicity occurs. Next slide. So, in terms of pond management, I think we've already heard these things. Maintain the density below 10 to the 4th colony forming units. And we do that by minimizing the organic load. And of course, there are many ways to minimize the organic load. Avoiding overfeeding, using probiotics to digest the organic matter in the pond. Some groups in Malaysia are having great results just with a very effective probiotic, from what I understand. And then the shrimp toilet idea, removing the sludge and putting it into a reservoir is an amazing innovation. Excellent. And then we heard about the polyculture with tilapia, and that's become popular, especially in Vietnam. And Dr. Loc Tran has introduced that with very strong success. But there are a lot of complications. The water has to be conditioned for quite a long period of time, 4 to 6 weeks holding period to condition the water. Okay, thank you. Yeah. But anyway, and then Robbins pointed out that tilapia can be used to feed on the sludge from the shrimp toilets within a recirculating pond system. So it all sort of fits together. Next slide, please. Well, this is the part one of the few parts that maybe Robbins didn't cover, and so I'm glad to have one little morsel to share with you. So this is the actual production results in Mexico. As you'll recall, Mexico was also hit by EMS around 2011. And these different colored lines are the different states in Mexico where production occurs. And the number 1 producing state is Sonora in the northwest. It's this one. So we'll use this one. Oh, that's the total. This is Sonora, yeah. So the key factor to look at is that the industry hit a rock bottom in 2013, and they pretty much recovered to the same level as before EMS hit. They're almost back to normal. So Mexico has almost totally recovered. So how did they do that? So that's the way they did it was by using a genetically resistant broodstock. And that's one of the fascinating things that we wanted to try in a collaboration with Blue Archipelago. So that's one of the few things we can report on that maybe you haven't heard before. So would you like to talk about that?
Seperti dah dipaparkan tadi, menunjukkan keadaannya di Mexico, di mana Mexico juga dilanda oleh EMS pada tahun 2011 dan pada tahun 2013 yang paling teruk sekali. Ya. Jadi bila saya dapat tahu tentang apa yang telah berlaku di Mexico, inilah mulanya kita bekerjasama dengan pihak.
I think what Bakar was saying was that of the 2 farms, there's a huge difference in the performance results. At the Kirpan farm, there's this history of relatively low yields, whereas at the C2 farm, excellent yields. And the C2 farm could stock EMS-infected post larvae and not get the disease. At the Kirpon farm, no matter what kind of post larvae, it would get the disease. And yet, everything was the same. Post larvae were the same, management was the same, feed was the same. The only thing different is the water. It's kind of like Robin's example of the farm that was taking water directly from the ocean on one side of the road and using well water on the other side of the road. In this case, we analyzed the seawater used by both locations, and everything was almost the same. All the minerals, the alkalinity, hardness, everything, pesticide presence, we looked for everything. The one huge difference was the organic load, measured as the biological oxygen demand. And you can see that it's over 10 times higher at Kirpon than at C2. So big difference in the organic load in the water, which predisposes it for EMS. So anyway, that was the scenario. It would be easy to do an EMS trial at the C2 farm and expect to get good results. But to do one at the Kirpon farm is the real test to see if something will work. Next slide, please. So let's talk about all the things that have been tried.
Sejak tahun 2012 di ladang kita di Kirpan, ya, kita dah cuba banyak inisiatif.
First set of data, I think probably there are more data now, but this was the set that Bakar presented at the GOAL meeting in Vancouver, Canada, just about 3 weeks ago. And the blue bars are from 12 SPR ponds, and the green bars are from control ponds. And when I say control, these were animals that either came from our normal Kona Bay broodstock or from SIS broodstock or other sources of broodstock. We call that control, and it's a mixture of the broodstock that are typically available in Malaysia. And the remarkable thing is, you just look at the tonnage, 7.7 tons per hectare from the SPR ponds and 2.6 from the control on average. And then it's all driven by survival. The survival is the key value. And look at 84% survival from the SPR ponds and 37.8% from the control ponds. And of course, if you get higher survival, that's going to lead to more tons. But even the growth rate was improved with the SPR animals. And overall, it means profitable ponds versus not profitable ponds. So I think that what we've learned today is there are some new approaches like the shrimp toilets and keeping organic load down, and those are things that have tremendous potential, and we want to try those, but it'll take time to implement those kind of capital improvements across 190 ponds. And so what we'll do in the interim is to stock as many SPR ponds as we can, because they're immediately profitable, and then we'll see if we can go from there. Before we go on to EHP, let me just say that there's this thing between SPF and SPR, and Kona Bay has always focused on SPF. And beginning in 2011, we were interested in finding whether there was really a white spot resistant line from South America. And one of the reasons was that in GAA, we actually published a paper by a group from Panama where they did lab trials with Dr. Leitner showing that they did indeed have white spot resistance. And so we were curious, and so beginning in 2012, we took samples of shrimp from Mexico, Honduras, Panama, and Ecuador, and we did white spot challenge trials at Dr. Leitner's lab, and we proved to ourselves that indeed there was white spot resistance. And then in 2013, we went through a process of primary and secondary quarantine. It took about a year and a half going through all the proper channels, and we got one of those stocks into Hawaii. And at the same time, Mexico imported some shrimp from Ecuador, and they also imported those shrimp to get white spot resistance. But to everyone's surprise, those broodstock were also resistant to EMS. Just blind luck, really. In Ecuador, when white spot hit in 1998 or 1999, they had no way to implement biosecurity. So in Ecuador, they just began breeding the survivors of a white spot outbreak every generation, and now it's 16 years later, and their animals are very resistant to white spot. But actually, if you think about it, they're breeding for whatever diseases are present in the pond. So whatever bacterial diseases were present in those ponds, their shrimp also developed resistance to. So in a way, it's not so surprising that that stock is not only resistant to white spot, but to other diseases, including bacterial diseases. So at Kona Bay, we focus on the SPF approach, but we're very intrigued by the success of Ecuador with an SPR approach. So here in Malaysia, we're trying to work with Blue Archipelago and study the ability to develop tolerance to diseases by working right in the presence of the diseases. So we want to see if we can improve the EMS resistance and maybe also the EHP resistance by breeding right in the presence of the disease. So when you hear us talk about SPR, it doesn't mean that we don't believe in SPF. We want to try both approaches. And SPR has a few advantages over SPF in terms of the speed of progress that you can make. Because not only can you test family advantages, you can also utilize individual differences in performance, which you cannot do in an SPR approach, or in an SPF approach. Anyway, we can get more into that if you like. Now let's go to the EHP. So once again, I think Robin's already covered this very well. It's a spore-forming parasite. It impedes digestion, so it causes slow growth. Next slide, please. I found an interesting book about microsporidians, and there are a few diagrams in there, and this schematic diagram on the right, let's see. It's very interesting because it shows the thick wall as two layers, protein on the outside, chitin on the inside, and then that coiled thing that looks kind of like a rib cage is actually a long tubule. And if you see the tubule here where it's extended, that's actually how this spore injects its germplasm into the host cell. In fact, some of the literature calls it a harpoon. It's like a long spear that's hollow. They call it It's like a combination of a harpoon and a hypodermic syringe. And so what actually happens is when the spore gets in the presence of the right environment, let's say in the gut of a shrimp, its vacuole right there, this big gland in the shrimp begins to swell. And it's just like a CO2 cartridge. It builds up huge pressure within the spore until it finally ruptures, and that tubule everts out like a harpoon and penetrates the host cell and injects the genetic material. Next slide, please. So it works like this. You see the spores on the left, and then the tubule everted. The genetic material goes into the host cell. Then that genetic material propagates, multiplies, and then the spore walls form, and then the cell ruptures, and then it does it again and again and again until it begins to really seriously affect the digestion of the shrimp, because all of this is happening in the epithelial cells of the hepatopancreas. Next slide, please. So at the goal meeting in Ho Chi Minh City 2 years ago, Dr. Flegel from Mahidol University in Thailand presented this slide. And what he was explaining was a study in Thailand looking at 200 Thai ponds to see what is the incidence of EMS or APINs. As you can see on the left side, it was 24% of those 200 ponds had APINs. But the remarkable thing is he found every one of those numbers of a sample that's highlighted in yellow is one that also had EHP. And so you can see on the right there that EHP was actually double the incidence of EMS in Thailand in 2014. It was already much more prevalent than EMS in Thailand. So that's what's been happening behind the scenes. It's a very, call it insidious or kind of a secretive disease. Very hard to detect, and it's gone unnoticed. And once it establishes in a hatchery, everything that passes through that hatchery is infected, and one hatchery can stock many ponds, so it's easy to see how it multiplies. Do you want to say a few words about that? So much about that, and we've all been wondering whether that's really EMS. So we took samples from 6 locations in Andhra Pradesh, and we sent them to Dr. Leitner's lab, and we analyzed for white spot, IHHNV, TSV, yellowhead, IMNV, EMS, and NHP. And they were negative for everything except EHP. 4 out of the 6 were positive for EHP. Also, white feces in that study were positive for EHP. Also, shrimp with loose shell were positive for EHP. So, at least a portion of what's going on in India is with running mortality syndrome is, we think, related to EHP. Next slide, please. So I think, once again, Robin's covered the main methods of transmission of EHP. Mainly it's oral, passed through the food, but also the same mechanism that happens with EMS, the vertical transmission caused by use of live foods. And the huge factor is that this spore is resistant to chlorination. So when the hatchery thinks it's disinfected its tanks, it really hasn't. It's not effective. Next slide, please. It can be diagnosed by wet mount or histology or PCR. And you see on the top, that's using 40x power of the objective. So when you count the 10x that you get from the ocular part of the microscope, it's actually 400. And one on the bottom is 100x, 100 power of the objective. plus the 10x of the ocular makes 1,000. So you can see it even on 40 power. And actually it becomes very fast, very easy, and very efficient. And the Blue Archipelago technicians have learned how to spot EHP and wet mounts. And it's a very fast and efficient way to identify it. Of course, PCR is much more sensitive, but more expensive, and it takes a little more time. Next slide, please. So, the methods for disinfecting a hatchery and a farm are pretty well described in a paper written by Dr. Flegel from Mahidol University, and I'd be happy to forward that document to any of you. It describes exactly what strength of an alkaline solution is needed to disinfect a hatchery. In this case, Dr. Flegel is recommending using sodium hydroxide, but we found here in Malaysia, sodium hydroxide is very difficult to get because it takes a skilled, authorized person to deal with that. And so a better alternative, easier to get, would be an acid here in Malaysia, unless you have a person who's authorized to use sodium hydroxide. And then after the treatment with either high pH or low pH, either one, then using chlorination. Chlorine with acid added is a more active form of chlorination. But this method is laid out in a paper by Dr. Flegel. If you'll approach me afterwards, I'll be happy to send you the document. Rootstock has got a high load of EHP, then even if your hatchery is clean, it'll immediately become recontaminated. I want to mention that IAQUA and Blue Archipelago are starting some efforts to try to breed for resistance to EHP, because within a pond we certainly see animals that grow to a much larger size that seem to have greater tolerance for EHP. So we'll test that in the very near future. Once again, maturation feed is the huge issue, not to use live feeds. At the very minimum, they should be frozen. Dr. Flegel recommends pasteurizing or using gamma radiation or using pellets. But frozen would be the bare minimum to try to deactivate the EHP. And then disinfecting the ponds, once again, Robin's already pointed out, it's calcium oxide. This method, I'd be happy to send you that method. Once again, it comes from Dr. Flegel's publication. It's just a couple pages, but it very clearly describes how to disinfect an earthen pond. And then, of course, from a pond point of view, the post larvae should also be free of EHP. And you can test that by PCR. So, we've kind of gone through EMS and EHP. I thought it would be good to go through one other exercise, and this is a biosecurity plan. If you have your own hatchery or you have your own farm, then you should have a biosecurity plan, and everybody in your operation should know what the plan is. And so let me just go through the steps. First, you identify the hazards. Then you assess which hazards are the most important, have a risk assessment. Then you determine how you're going to manage those risks, and then you communicate it. Everybody should know the plan. Everybody in your operation knows what to do. And then at a higher level, for example, with the Department of Fisheries, how to do a biosecurity plan for a whole zone with multiple farms so that a whole zone is protected. So these, if you look at biosecurity plans, whether it's for salmon, koi, or shrimp, they're all very, very similar. The typical hazards are, number one, the animals. The animals might be infected. Number two, the water. then it's equipment, it's animal health, that would be, for example, genetic resistance, or maybe use of immunostimulants in the feed, vectors, people, and then management. So those are the standard hazards. Now, here, we've just taken the liberty of identifying which are the critical ones. So these are the critical ones for both EMS and EHP in the hatchery. Number one is the broodstock source. So you have to use broodstock that are free of those diseases. Number two is genetic resistance. If possible, I should learn to use the word tolerance. Genetic tolerance. Use animals that are tolerant of the disease, that can give you higher survival. So, Robbins mentioned that some animals are more tolerant of the EMS toxin. We found the same thing. Same experience that Mexico has, works in Malaysia. So there's a big genetic component for resistance or tolerance. Then, disinfecting tanks and equipment, making sure the water is disinfected, and then that huge one of not using live maturation foods.
Okay.
Incredible, tremendous amount of information. And you've also had a chance to listen to Bakar, one of the CEOs of one of the largest shrimp farming operations in Malaysia, telling you about his experience. But what about all the people and what about all the shrimp farmers in Malaysia who couldn't be here? How do we get the message out? So I want to mention that the Global Aquaculture Alliance formed a foundation called the Responsible Aquaculture Foundation, and its purpose is education and training. So we're developing learning modules, basically taking the information that we've presented today on EMS and EHP and putting it in a form where you can access it online. You can access it online, and it's like a classroom. If you read the material, there's a little learning check at the end. If you're more cynical, you could call it a test, and to see if you were paying attention. You take the module, pass the test, you get a little certificate. It means you now are qualified for that particular learning module. And we hope we can do many, many of these. But I hope we can work with some folks in the Department of Fisheries and maybe get this translated into Bahasa so that it can reach a broader audience. Because we've been fortunate to have some great information, but frankly, the speakers here won't be able to visit Sabah and Sarawak and everywhere in Malaysia where the information is needed. So the efficient way to get it out is an online platform. I think that's it for me. I'm going to hand it off to Bakar to see if there is anything else he wants to cover, but thank you very much for your attention.